Hi everyone, and welcome back to another video where we want to talk about text modeling with a focus in the financial domain. However, this video is going to be more of a general video because in the past videos we've been mostly seeing text modeling techniques that kind of depend on the counting of terms in documents. And now we want to move forward to, I would say, maybe more state-of-the-art language models, and they work differently. And what they usually all have in common is that the way how they derive numerical representations of text is often based on neural network architectures. And this is why before we start talking about new text and language models, we are taking a short introduction to neural networks in general, because I think and I hope it helps for a better understanding of the text models that we're going to discuss afterwards. All right, so without saying anything more about this, let's dive into the introduction into neural networks. By the way, I am always linking the notebook in the description below, so you can access that for yourself if you are familiar with Python. And here in that case, I'm going to use pytorch. There are also other packages such as TensorFlow, which can be very helpful if you want to conduct neural network operations and train them and so on. But here in our example, we are going to use pytorch, which I consider to be a little bit more popular, especially in the academic and research area. All right, so we are only talking here about what could be seen maybe as the benchmark or fundamental neural network. So I think mostly if people talk about neural networks, they mean those neural networks which are, to my understanding, forward neural networks, or also fully densely connected neural networks. And if you never heard about them before, okay, so I'm trying to explain this like if you never heard about them before. If you did, and if this kind of gets boring, then just feel free to forward in the video. But if you never heard about a neural network, there are different angles how we can approach what it is. And let's first say what it usually consists of. And a neural network usually consists of what is called layers. So it has multiple layers. And each layer has usually multiple what is called neurons. And the way how the neurons are calculated is in the setting where we have a for network, always more or less the same thing. And we have two mathematical operations that are kind of always repeated here. The first one, I think, is called officially an affine transformation. It looks very like of what you maybe are used to, which is the regression line of a regression model. And then the output of this calculation is then usually inserted what is called an activation function. And in most of the cases is a nonlinear activation function. Here, especially in this notebook, I'm try to use a proper mathematical notation. If you're used to these kind of notations, I think it's helpful. If you're not, then maybe not, or maybe you can use this to start learning things with mathematical notation, because this is in general very helpful. So neural networks are obviously often used with data, and even though our data is going to be text, I would say in most of the cases the data is numerical. Okay, so in our example that I'm kind of using here in this notebook, let's assume you want to develop a model which kind of predicts the actual value for real estate. And in your data sample, you collected the value or the prices of certain real estates and some attributes of the real estates. So for instance, it could be the number of bathrooms, if you're talking about houses. It could be the distance to the next city center. It could be the age of the house. So those are attributes for which we maybe assume that there's a certain relationship to the actual value of a real estate. And what in this scenario a neural network is supposed to find out is, or to approximate, is the functional relationship between those attributes and the real estate value. And so in this first, so the input data is called in that context is simply the input layer. And also like the realizations of those attributes, such as the number of bathrooms, like the distance to the city center and the age of the real estate, those are then, in our example here, already the neurons of the hidden layer. Okay, so this is special because only the neurons of the hidden layers are usually values that we actually can collect or that we can observe or that are included in the data sample. But yeah, to have a consistent notation here, we also denote the input data as the neurons here. So if we have then, for instance, p different variables in our data set, h1 would be the value for the first neuron, so again the number of bathrooms, h2 would be the distance to the city center, and then the last variable in our case would be the age of the real estate. And then what is always done, so let p then denote here like the number of neurons, and in our setting in the input layer it's the number of observable variables that are used for predicting real estate values. And then what we first always do is we conduct this mathematical operation here. So basically, as I said, this is kind of, if you're used to linear regression, this is the first part of a linear regression model, which is also called the regression line. And what it basically does, it kind of weights the values of the variables here, okay? Because the W1, W2, WP, those are called parameters, as well as B in the setting of a regression model, that would be the constant, and usually you would be using beta instead of W. But what those things are parameters of the model. In the beginning, you can picture them to be, you can choose them maybe randomly, but then later, those parameters are calibrated in a way such that our predictions are close to the actual observations in the data set. However, for the moment, you can picture them to be given numbers. And obviously, for instance, if you have a positive W1 here, and if it's a large number, and you multiply it with the number of bathrooms, then you give the number of bathrooms a higher weighting, especially, for instance, if W2, for instance, would be a very small number. Okay, so basically what you build here is a weighted combination of the input neurons, and then B here, the constant, just gives the model more flexibility. Sometimes you can also do not use this and just use the weighting here. So basically, I would say still this is kind of a simple mathematical operation. Everyone kind of is used to multiplying numbers and adding them. But this is always the first step. Here, I think it's important just to understand, if we write it down like this, what we mean is, this is how we would treat a single observation in a data sample. And then here, very likely, the result is going to be some real valued number. And then the next step for a neural network is then to insert this real valued number into another function, which is called the activation function, and here denoted by G. Okay, so then if you insert that value here into another function, you get the output. Congratulations, then you calculated the value of the hidden neuron for the next layer. And as we have multiple layers, I kind of use this notation here. So one just says, okay, this is the value that comes from the variables in the first layer, and then these are used to create a neuron for here then the second layer. Okay, so that's the value in the superscript here. So if you write that down in a more general notation, then we coming from this equation here to that one here, but it's exactly the same. It's just with maybe a more complex looking notation, but it's a cleaner notation here. And so maybe let's pause here for just a second. And again, I think this is just important to get it right from the start. So we always have these two operations. You have some numbers, which are the neurons. In a general explanation, that would be always the neurons from the previous layer. So if you start with the first layer, which is the input layer, then those are the neurons here. You calculate a weighted sum of those neurons, you add another number here, and then you insert that into what is called an activation function. The activation function is something that you can decide what it is. We're going to take a look later in the concrete example which type of shape an activation function may have. For the moment, you can picture anyone, okay? Even though it doesn't make sense in that context, but you can say, for instance, okay, let's say the activation function would be the exponential function or the natural log function, or I don't know, x to the power of 2 or something like that. All right. And as this is kind of a very flexible thing, obviously you can do this multiple times. And if you do this multiple times, but with different weights here, so with different parameters, obviously the result here will be different, and also the calculated neuron will be different. But that means you can for as many times as you want, using different parameters, create new neurons. And this is the very characteristic thing for neural networks, because you will decide how many neurons you want to create. And if you're being specific here, usually in a forward neural network, what is coming after the input layer is what is called the first hidden layer. So for instance, if we say, okay, our input data has 3 feature variables, again, feature variables in that example, I mean number of bathrooms, distance to city center, age of the house. You can choose, okay, let's say for instance, I want to create 5 hidden neurons for every observation. Then you need 5 sets of W parameters here and 5 values for B here, right? But also you can say, okay, just want to create 3 or 2 or 10. That's a choice which kind of defines the architecture of the neural network here, right? So if we move forward here, so that is just really the very general definition still for a single neuron. Here L minus 1, L is the number of the layer, and K, or like here, like those values here then are the P is the number of the neurons in each layer. I think it takes some time to study that kind of notation to really get the idea. But what you basically have for a real data sample is that you will have multiple observations, and for every observation you will use the same parameters and generate a number of hidden neurons that you would like to create. Okay, so to get a better understanding, let's take a look at a numerical example here. So here, those are just some random numbers I create here because I don't have any reasonable data set with real estate values at hand. However, you could picture this, for instance, even though the numbers are rather meaningless in that example, that would be the realizations for the first variable here, that would be the realizations for the second variable here, and that would be the realizations for the third variable here. And here that would be all 3 realizations from the first observation, the 3 realizations from the second observations, the 3 realizations from the third, and here from the fourth observation. So that would be our whole data set in that example. So we have a data set that includes 4 observations and 3 what is called feature variables, right? So that would be not include the value of the real estate, but those would be the attributes of the real estate. And then in the first step, to create, let's say, 2 hidden neurons for the next layer, what we always would need, we would need to, generate this weighted sum of those input values with 2 different sets of W parameters and add always our B constant value to it. And then also insert this result into the activation function, right? So Torch includes a certain modules and class definitions, which are really helpful in this context. So the NN linear from the NN module function is exactly what is executing exactly this thing. So that means if we execute it like this, what we don't see are like what is internally being calculated here, but this is what we're going to take a look at now. Okay, so if you define this here, would be the weightings or the parameters. Okay, so what you see here would be like in the first column would be the weights that are used to generate the first hidden neuron, and what would be in the second column here are the weights that are used to generate the second hidden neuron. And also we can take a look at the bias values. The bias, so the B, which is always used to create the first hidden neuron, for every observation is this value, and the one, the bias value with this here, as you can see here, is the one which is used to create always the second hidden neuron, again, for every observation, okay? So if we, let me go here, so that would be our data input. Then this add symbol, as we can see here below, just conducts a matrix multiplication. So if we just multiply them with the weights here, so what this does here is, if we have our input data, as you can see here, then, and if we have our, the weights here, so to calculate this number here, right? So this is just matrix multiplication. I hope you're aware of that, but just one more time. So what you will do here is you multiply this times this plus this times this plus this times this, okay? And that should hopefully add up to this number here, because this is matrix calculation. All right, so if we do this here, then this is what results. And also then to every calculated weighted sum here, we are going to add the corresponding bias value here. Okay, so to the like every weighted sums for the first one, we add the first biased value, and to the ones from the second one, we add the second biased value. This is called broadcasting. It's not really in line with matrix multiplication, but again, this is just to demonstrate and showcase the mathematical operations which we denoted above or explained above and defined them to be this affine transformation. Okay, so that would be then the result here. So you can see, so here is that we really define this function. This is how we take a look inside its weights, into the parameters and the bias. This is how we manually would calculate this by just, conducting this matrix operation and multiplication. And this is how you would really do it, or like how you can do it with the internal method that comes along with this function here, with this class instant here, sorry. And then the output, so those numbers here, they kind of stem from a model that is only captured to capture linear relationships. Okay, so what I mean with this, we always have this kind of relationship here, and this is simply a linear relationship. And in real life, especially for real estate, for instance, there may be also like non-linear relationships between the input feature variables and the real estate values. And to give our model the capability to capture those linear those linear relationships, we kind of transform the values that before we create, we finally have the hindrance, we transform them potentially in a non-linear way, right? So for instance, if I think we can take a look at the documentation here. So here, if you are interested in PyTorch and if you don't know it, this is kind of its landing page, so pytorch.org. But here then we go to the docs and the documentation to PyTorch. And here on the left, we can see there's the NN module. And then here on the right, we can see there are the nonlinear activations. And here is a bunch of nonlinear activation functions that are implemented within the PyTorch package. And if you want to play around with that, you can, for instance, replace the name of the function here with another one. So for instance, here we have the ReLU function. We can take a look here, for instance, also at the ELU. You would just need to replace that here, and then it shows you what this does. And here it's important for you to understand what is on the x-axis here. You can maybe add this here. So we have the x label, and in our notation that would be Z, right? So this is the weighted sum of the neurons from the previous layer times the bias. And here on the y-axis, of course, we have g of that value. Okay, and g here refers to the activation function. And as we can see here, this is really just non-linear, right? In terms of linear would be a line in that case here, and non-linear. So a line means wherever we are here on the x-axis, increasing or decreasing by 1 unit will have always the same impact on the outcome of the function. Instead, for a non-linear function, if we are, for instance, here, and if we increase the value, then the increase in the function value is way smaller than, for instance, if we are here and increase by the same amount, the set value in that case here, right? So, but this is to give the model the flexibility and the capability also to learn about nonlinear relationships between the input features and then later on, for instance, what is called the target variable, so in our example, the real estate value. All right, so and then finally, if you take a look here, so this is how the values for the potentially new hidden neurons. So these are, the first column are the like the first hidden neuron for every observation, and the second column is the second hidden neuron for every observation. Then if we pass this through the ReLU function, okay, so let's go there. So if the ReLU function, even though without taking a look at its mathematical definition, you can see what this basically does. It is if the original value is smaller than 0, then it gives it just the value of 0. And if it's higher than 0, then it's exactly the same value as you inserted into the function. So basically, it's kind of the maximum between 0 and the function input. And if we do that here, you can compare the outcome. So here we can see everything which is a positive number remains that number, and everything which is a negative number is becoming a 0 here. All right? Okay, to keep the videos as short as possible, but I guess already this video has been quite long again, let's stop here and then continue in the next video and how to define a neural network using PyTorch. And yeah, I think that's what we'll see in the next video and after that. So this kind of being a mini series about neural networks within the series of text modeling. And then we, after we're done with those videos, we're going to continue with language models that are built upon neural networks. Okay, but here for the moment, grab a coffee, make a pause, whatever, and then come back hopefully to the next video, which will shortly tell you how you would define a neural network. Now that you know how you can create a new layer with hidden neurons out of a previous layer. So in our example so far, out of an input layer. All right. See you in the next video and take care. Bye bye.